this example, we're pulling a metal bar, so it's a conductor, through a magnetic field. The dots represent that the magnetic field is pointing out of the page. We're moving with a velocity as shown, moves down. And the question I wrote down, draw the induced charges on the bar. The slide you have says pick which one is correct, a multiple choice. But I figure maybe we're a little better off trying to see if we can figure out what the answer is. So let's ask what happens to a positive charge. Let's ask what happens to the negative charge, and then we can see where do the charges pile up. So every little positive charge on this in this bar is going to feel a force. Let's see if we can find the direction of the force. We'll do V cross B, so our thumb is V, our finger is B, and then our force, our finger, points to the left. So the force on the positive charge points to the left. There's the magnetic force on that guy. So that tells us what happens to the positive. So we probably know right off the bat what happens to the negative, but let's do it anyway. So we do V cross B to give our force. So that's the direction of the force on a positive charge. A negative charge we have to rotate by 180, so the magnetic force points the opposite direction. So if our magnetic force on the right, on the positive charges, is to the right, it means that our positive charge will move to the right, and our negative charge will move to the left. So this is the induced charge separation due to the motion in that field. For you guys, I think that's option B if you're looking at the posted slides. Okay, next let's do one that has a little bit more meat to it. Let's have a metal bar. It's got length L, so from here to here is a length L. Why don't I draw that in? It's rotating with angular velocity omega about a pivot at one end of the bar. So I'm going to put my pivot right here. I'm going to say that it's rotating this way. There's omega. The picture doesn't really show it, but let's say that this bar is in the magnetic field the entire time. So this magnetic field extends everywhere. And our uniform magnetic field B is perpendicular to the plane of rotation, points into the page. Find the potential difference between the ends of the bar. So this is a little bit like what we did when we found our equation that the induced potential was BLV, but now the situation's a little different. This time it's rotating, so we have to ask, what does that do? So let's draw a little positive charge. Let's ask what happens to it, see if we can figure out the nature of what's going on with the charges, and see if we can sort that out to find the potential. So a little positive charge, if omega is going this way, the velocity at any one time is a tangent to the circle, so points in the direction of the motion. So we have V cross B shows a magnetic force pointing to the top end of the rod. So that's going to cause a charge separation where we'll get positive charges piling up here. There's our FB and our V. Our positive charges pile up here, our negative charges will pile up down on the bottom. So now we see there's a potential difference across the two ends of the bar. The top end, this is going to be our high potential, our bottom end is going to be our low potential. When we reach steady state, when the charges are no longer in motion, we get that the net force is 0, and the magnitude of the magnetic force is equal to the magnitude of the electric force. So QVB equals QE, the Q's cancel, and we're left that the electric field, the induced electric field, is equal to the velocity, the linear or the tangential velocity, times the magnetic field. Well, this tangential velocity is a little bit funny because it's different at different places. So how are we going to write down the tangential velocity? So let's remember circular motion. And in circular motion, we know that the tangential velocity is the angular velocity times its distance from the pivot. So from here to here is the distance from the pivot. Okay, so that incorporates the tangential velocity with the angular velocity. Next, let's ask, from velocity, electric field, distances, how do we find electric potential? Well, electric potential, let's call it delta V, is equal to minus the integral of the electric field dotted with the distance. So our electric field points this way, our distance points this way, so we've got ER, the radial component of electric field, times the radial distance from here to here. The limits of our integral, let's go from the long end of the rod to the pivot point of the rod. So let's go from L to 0. I'm picking it that way so that our dr and our electric field point in the same direction. So we're integrating electric field over the length of the rod. So let's put in what we found for our electric field. So we've got minus from L to 0. Our electric field is E equals V times B, or omega R times B. So let's put that part in. And it's integrated with respect to R. We can take our omega and B outside. R dr. The integral of R dr is R squared over 2. That's going to be evaluated at 0 and L. So we get omega B 0 squared over 2 minus, oh, drop my minus sign, minus L squared over 2. And then that result gives us that our change in potential, delta V, now let's switch to Faraday's notation, equals our induced EMF epsilon, equals minus omega B times minus L squared over 2, which is omega times B times L squared over 2. Let's put this in context a little bit. So let's think about what that kind of tells us. Let's ask, what is the velocity at the middle of the bar? So velocity at the middle of the bar equals omega times the distance. So in that case, our induced EMF would be omega times L over 2 times B times L. Just rearrange this a little bit. So your induced EMF would be the velocity at the middle times BL. And that makes a lot of sense with what we said before, that our induced EMF was B times L times V. If we have a rotating object like this with a pivot at one end, the velocity can be approximated by the velocity right in the middle. Okay, there's a couple of examples. Next we'll move on to thinking about current. We've already discussed potential. Let's see where current comes in.